Let's take a look at what it looks like from a network provider's perspective to have a Science DMZ as a customer. So instead of looking at this from the perspective of the people deploying a Science DMZ on a campus, we're going to look at this from the perspective of the wide area network that has one or more Science DMZs connected to them and whose job it is to actually carry the traffic from those Science DMZs to other Science DMZs or other institutions. So for a Science DMZ at a research institution, several conditions have to exist in the wide area network. So the wide area network has to be loss-free to support TCP-based bulk data transfer applications. That means no packet loss, and that means sufficient buffering to avoid fan-in congestion and things like that. We need to have perf deployed so that test and measurement is available for ad hoc debugging and also for performance measurement over time to ensure everything's working correctly. And then we need adequate capacity because guess what? If you don't have the capacity, real-world congestion causes packet loss too, and that's as much of a problem as packet loss from any other source. It still causes performance problems. But there are some details involved in capacity for handling science flows that are a little bit different from capacity planning to handle a commodity network. So you have to think of capability, not just capacity, right? Can I actually inject a workflow of a particular data scale into the network with the network in its current state or not? And so that means looking at burst load, not average load. So if we look at the difference in traffic profile from two different interfaces, one graph, which I'm showing now, shows what it looks like on a commodity peering interface. So this is 7 days worth of traffic on a commodity peering interface. Monday, Tuesday, Wednesday, Thursday, Friday, all have this nice smooth haystack curve. And then Saturday and Sunday, there are no eyeballs, and so there's very little traffic. Now, if we look at a science network peering interface, right? So instead of facing the commodity network, this faces other science networks. There's no pattern. When the science workflow is running, there's data to move. When there's no science workflow running, there's less data to move. And this whole notion of there being this regular pattern that follows people's diurnal activities doesn't really exist in this case, or at least it doesn't show up in the traffic graph in any sort of meaningful way. So we can see already that there's a difference in behavior between commodity traffic and science network traffic. So now if we dig a little deeper and look into some of the load characteristics, we'll see some differences again. So here's another example of commodity exchange traffic, Friday to Friday. So it's Friday and then the weekend, and then some nice web and email haystacks again. Monday through Thursday are a little higher than Friday. I guess some people telecommuted on Friday, or maybe some people took Friday off because they were going out for the weekend or something like that. But now you look at the R&E peering exchange, and again, it doesn't provide any insight as to when the people were in the office and when the people were not in the office. Now, this is a 10 gigabit interface, and if we look at Wednesday, so this is Friday to Friday, so Wednesday is going to be the one there with that peak in it. Those two peaks turn out to be very, very different than they look in this plot when you look at them under more detail. So at a 1 week resolution, most plotting packages are going to do a whole bunch of summary of the data, and so you're not going to see all of the fine features. You're not going to see the peaks being as high because they're going to be averaged out. So if we blow up that Wednesday detail, we start to see that the workflow is a lot choppier than that 1 week sort of aggregate view might have shown it to be. And so you see there's this really spiky part at the leading edge. If we zoom up on that, it looks like a data transfer workflow that bursts for a few minutes and then waits for a few minutes and then bursts for a few minutes and waits for a few minutes. There is 6 gig of load swing for that workflow. And so it's very different when you consider building a network infrastructure to accommodate the sudden injection of a workflow like that. You have to make sure that you can handle the sudden injection of a workflow like that while maintaining a loss-free infrastructure in order for it to be effectively useful to support data-intensive science. So this gets back again to maintaining enough headroom for burst capacity, and it goes into capacity planning. So if all you look at is average numbers, 1 day averages or 1 week averages, that's not going to give you an accurate representation of the amount of capacity you need to support the science workflows that you've already got, let alone for future growth, because you won't see those large peaks because they'll have been summarized by taking an average view. So from a network provider perspective, a Science DMZ is a very demanding customer, and it requires some thinking to ensure that you're accounting for it correctly.